eutectic temperature. When I add my additive, on the other hand, I lose that. The freezing point just drops and drops and drops. But again, this is not a true freezing point of water. What's happening is the liquid, rather than showing a nice, well-defined freezing, is just getting thicker and thicker and thicker due to the effect of the cryoprotectant additive. So we need to be a little bit careful about freezing points with organic additives present. So what value do we get from organic type additives? Agricultural additives are effective corrosion inhibitors. If they provide some viscosity to the liquid, they can help to keep the treated salt or pre-wetted salt from leaching. There have been reports that these sorts of additives provide some increased residual effect. There may be some improved anti-icing because of the anti-freeze effect, but what you're not going to see is improved ice melting. At least in all of the agricultural or organic additives I've tested, I've never found one that resulted in increased ice melting at colder temperatures. So if we want to actually boost the low temperature ice melting of brine, we really need to rely on magnesium chloride and calcium chloride. And so let's next talk about how much boost do we actually get in ice melting power from a hot mix. We've run some experiments to try and determine this. And to do this, we developed an improved ice melting test method. I don't have time to go into, I could give you a whole talk on just that by itself. I don't have time to go into a lot of detail about the development of this method. We worked together with the Western Transportation Institute at Montana State University. We published this research a few years ago at the International TRB conference. I'd be happy to send that report to you. You can grab me. I'll be over at the Cargill booth later on. You can give me your contact information. If you're interested, I'd be happy to send that to you. But basically, it turns out that the standard SHRP ice melting capacity test has got some imprecision to it. And so we did some work to improve the precision of that test by making what I call an ice cube titration test. And it's rather simple, actually. All we do is we freeze ice cubes onto strings, and we immerse them in beakers of our various de-icer liquids that are held at a given temperature in an environmental chamber. And all you do is you keep adding ice until ice won't melt anymore. Now you weigh the beakers, you weigh them before and after. You can very precisely measure how much ice is melted into your brine by the difference, and you've got a precise measurement of ice melting capacity. Now, we did the following experiment to look at hot mixes. We compared the amount of ice melting from equal quantities of plain salt brine, plain mag chloride brine, and a 20% hot mix, 20% mag chloride plus 80% salt brine. And this is what we see at a temperature of 5 degrees Fahrenheit, so fairly cold. Note that we get much more melting from mag chloride brine than we do from salt brine at 5 degrees. So far, so good. That's just what we would expect because we know mag chloride is going to be a better ice melter at colder temperatures. Now, here's what I think is interesting. What is the benefit that we get from the mixture of the two? Is it just additive, or is there some kind of synergism going on? If it's just additive, a 20% hot mix should have 20% of this ice melting capacity plus 80% of that ice melting capacity. If we calculate that, that's what it looks like. Note that when we experimentally measured it, it was identical. So what this tells us then is that when you make a hot mix of calcium chloride or magnesium chloride, you get just what you pay for. There's no magical synergism going on that causes the mixture to be more effective than the individual components would be if you put them down separately in terms of their ice melting power. So the more calcium or mag chloride you add, the more ice melting you're going to get at cold temperatures. But you're just going to get just what you pay for. Of course, the next question is how much is enough? And that's a question that is more difficult to answer precisely, as we talked about earlier. The ultimate answer to that is going to depend on continued field experience, as well as development of improved test methods to better simulate how much is actually needed under various field conditions. But just wanted to point out that the way these work is not synergistically. You get just what you pay for.